Right now, there are around 18 commonly held interpretations of quantum mechanics. Which one do you think works best and why?
Well, I think it's fair to say that actually no one really understands how to interpret quantum mechanics because in many ways it's just completely unlike the normal universe we're used to dealing with on a macroscopic scale. In many ways, the key experiment in quantum mechanics is the double slit experiment, where you get the interference pattern if you're dealing with waves, and you get an interference pattern when you put an electron beam through. So electrons are behaving like waves in some respect. And you can kind of imagine that if you have a whole load of electrons going through, maybe they'd behave like a wave. But you can turn down the intensity of the electron beam until there's only one electron going through a slit at a time. So then surely the pattern should go to being more like the ballistic little particles fired through a slit. No, each electron goes through and hits the screen at the other end, and there's a single flash of light corresponding to a single electron. But the pattern you build up, once you've run it for long enough that enough electrons have gone through, the pattern you build up is the interference pattern. So even though a single electron goes through the slit at each point in time, even though each single electron hits the screen as a single event, somehow it kind of interfered with itself and the electron wave went through both slits at the same time. How did it do that if it's a single particle that goes onto the screen? And so this then is the whole idea of how do you interpret quantum mechanics. By the time the electron hits the screen, it's obviously a single particle, and yet you're not meant to be able to say which slit it went through. Okay, so let's wind it back 1 microsecond. The microsecond before the electron hit the screen as a single particle, where was it? And that's where all these different interpretations of quantum mechanics come in. There's a realist interpretation that says, well, a microsecond before it hit the screen, it was just before that point. Quantum mechanics cannot tell you that. Quantum mechanics can only give you a probability of where it was. That means quantum mechanics is incomplete. And so all those hidden variable theories come from the fact we detect it here. Where was it a microsecond beforehand? And any physicist is going to say, a microsecond beforehand, it was just about there, just before it hit. Whereas, if you like, the orthodox Copenhagen interpretation of quantum mechanics says, no, it wasn't. It was spread out as a wave, actually across the entire universe. It had some amplitude, and you can't say where it was before it hit the screen. So that's the whole issue with quantum mechanics. There's this idea in the Copenhagen interpretation, the orthodox interpretation, that the wave, electron wave, had some probability of being anywhere in the universe, and that it's only the act of measurement that localized it. But why should the act of measurement localize? Why is there this very strange collapse of the wave function that localizes your electron wave to a single point? How did that work? And how could we even begin to describe that mathematically and physically? It's a very strange kind of idea.
So do you think that the wave function collapse is an ad hoc explanation of quantum?
It has to be added in, yes. It's not what you get. Your wave function evolves according to the Schrödinger equation, and that evolution is continuous in time. until you measure it, at which point there is no longer probability anywhere in the universe that you might find this electron. Actually, you have found this electron and you know where it is. And your subsequent measurement of the electron will be that it was just where you measured it. So where was it a microsecond beforehand? And that's the whole fun thing about quantum mechanics, that we all have this gut feeling that a microsecond beforehand, it was actually just really close to where we're about to measure it. Because how does it know it's about to be measured? It's one of these really strange aspects of quantum mechanics that we don't quite know how to interpret, which is why there comes all these different interpretations. So there's the many worlds interpretation, which says, well, the electron is actually kind of at all these points in the universe, and the entire universe has duplicated itself multiple times, in fact, so that the electron in some universe is just here, and in others it's out at Alpha Centauri. And really, I mean, have you never heard of conservation of anything? Entropy, mass, energy, anything. Let's duplicate the entire universe. No, please, let's not. So that seems to me one of the least successful interpretations of quantum mechanics, but because it's also one of the, in some ways, most mind-blowing and quite bizarre, it's one of the ones that's beloved by sci-fi.
Okay, so if any given interpretation of quantum mechanics has no experimental evidence, should we as physicists be concerned about which interpretation is actually correct?
That's a very interesting question. So a famous way of encompassing the Copenhagen interpretation is the shut up and calculate idea. Shut up and calculate. Come on, we know Schrödinger's equation works. This works. Shut up and calculate. Yes, to some extent. However, physics is not just being able to calculate things. Physics is being able to understand. And given the state of our fundamental understanding of how to interpret quantum mechanics, no. We should be thinking about the interpretation, and we should come up with something a little more viable than some of the ones so far. But having said that, it's not a purely... it is a question that can be addressed by experiment. So in some sense, the question, where was the particle just before you measured it? Well, if you'd measured it a microsecond earlier, then you could have measured that, but then you're into the collapse of the wave function, and what has changed? And the answer is nothing. However, there's some very subtle ways of testing quantum mechanics to do with spin. If you make an electron-positron pair out of two photons, then one's spinning up, one's spinning down. And this is correlated. You can't say, quantum mechanics says there's some probability that the one on the left is spin up and 50% spin down, but they're correlated. If the one on the left is spin up, the one on the right must be spin down, and vice versa. So what you can do is you can say, okay, so if that's true, then if I do an electron-positron pair, one spinning up, one spinning down, and if I then measure the one on the left and measure it to be spin up, then instantaneously, faster than the speed of light, which Einstein says can't happen, in quantum mechanics, instantaneously the wave function has collapsed, and I know the spin of the one on the right. Information traveling faster than the speed of light. Come on, we're good relativists. We know we can't do this. And that's sort of the experiment that they were able to do. So Bell's theorem actually has a number of these kind of entangled quantum states, and you can do statistics on it. And they actually managed to do this experiment. And the statistics came out, the quantum indeterminate one. So it is not true that it is just an arbitrary question. It's a question that can be addressed by experiment and has been addressed by experiment, in which case there is no agnostic position because the experiment is the experiment and the result of an experiment is an experiment. And so what we need to do then is understand how to interpret that result. But the result is that the universe can do this information propagating faster than the speed of light. The wave function did collapse. You see these correlations, and they tell you that if you measured that one spin up, and it's random, that one is correlated. And you can separate those experimental apparatus by a distance that's bigger than the distance that light would have to, the speed of light propagation. You can do it and measure the other one faster than the speed of light would have been able to propagate.
Great. So in 2013, in a poll of quantum physicists, about 42% said that they agreed with the Copenhagen interpretation, and 20% with many worlds. It was labelled as the most embarrassing.
20%
I know.
with many worlds. I don't see the universe splitting on every quantum indeterminacy.
So why do you feel there was quite a bit of disagreement within physicists as to what interpretation that should be followed?
Because none of the interpretations to date feels right. We're physicists, and we know the equations work. They're fantastic. We can calculate things about atoms. They give us the right answers, but somehow we know as physicists that we haven't got the right way of thinking about them. We haven't got the right way of thinking about the answers that they give. We have got the right way of calculating the answers, but in terms of thinking about it, no.
So if you don't have any experimental evidence for something, for an interpretation, then how do you actually go about determining which one is better? Because presumably you could have the most complicated theory imaginable about why quantum mechanics operates the way it does.
Yeah.
And you could have another one which is incredibly simple, but would you always prefer the simpler one in that situation? Or are there different things that you would appeal to?
I think there's a combination of things that physicists want to see in an explanation. Beauty, symmetry, simplicity. So things like general relativity. Einstein's equations basically say gravity equals space-time curvature. They're just a mathematical way of writing gravity equals space-time curvature. But there's actually many ways of writing gravity equals space-time curvature. Einstein just picked the simplest, lowest order one because as physicists, we go for the simplest explanation first. And it works incredibly well. But there's no reason why it should be the simplest one. But we're used to physics working that way. And even though you might look at the Einstein equations and think, she calls that simple and beautiful, really? But at the same time, underlying the mathematics, you can see this simplicity, this beauty that is always compelling for physicists.
Okay, great. So obviously the many worlds interpretation it's quite vague about
I think it's nuts. Let's go for nuts, shall we?
so when it's quite vague about when and how like universes will branch out. There's no real explanation to it. So what are your thoughts on that?
Nutters.
Quite simply.
Quite simply, nutters. I mean, really? No.
Okay.
I wonder if they have some deep psychological issues that they can't bear to make a choice. And so they'd rather there was a universe somewhere in which they'd made the other choice, and that...
Do many of your colleagues support the many worlds interpretation?
I have no idea, actually, because...
So they keep close to their chest.
Because quantum mechanics isn't what I research into, then in some sense I don't have those conversations. But at one point the Atmel group here did a seminar on the many different interpretations of quantum mechanics. And there's also a really good book by Jim Al-Khalid, who's a particle physicist, and he does a really nice popular science book on looking at the different interpretations. He likes Bohm's pilot wave theory.
Yeah.
If I knew more about it, I might be able to talk more usefully about it. But it seems to me that and he's a subject specialist, and he felt that had more possibilities as being a foundation for understanding fundamentally what we're doing in using Schrödinger's equation.
Mm.
So obviously working with black holes, you look at the universe quite a lot. So have you found any actual evidence of other universes so far?
Funnily enough, no. So again, it's a kind of halfway philosophical question, because if you're looking at an entirely other universe, then in some sense it's disconnected in space and time from our universe. So how would we have any knowledge of it? How could we do that? Well, in one sense, if we understood more, maybe we could answer that question. Would another universe manage to make some imprint, some observational imprint on our own universe? And if so, what would that be? What would that look like? And I think we all strongly suspect that answering that question would require us to have a better theory than the ones we have so far, in that quantum mechanics rather famously won't talk to general relativity. And this is unfortunate, because quantum mechanics is by far the best theoretical description we have of the behavior of matter on the smallest scales. Einstein's general relativity is by far the best description we have of the behavior of gravity. So, if you want to talk about the behavior of gravity on very small scales, you need a quantum theory of gravity, or a theory of quantum gravity, whichever one of those you care to call it. And we don't have one, since quantum mechanics won't talk to gravity. So, until we have that, then we can't describe what happens when you have extremely strong gravitational fields on very small scales, which is, of course, what you'd need to talk about the beginning of the universe. It's also what you'd need if you wanted to talk about what's at the bottom of a black hole. Is it a true singularity? Einstein's equations say that nothing halts the gravitational collapse to an infinitesimal point of infinite density. Actually, in physics, when we get infinities out of our equations, we tend to suspect we've taken them somewhere they didn't want to go and have gone outside their realm of applicability. And that sounds like we need a quantum theory of gravity to talk about what's at the bottom of the black hole, what's at the beginning of the universe. But if we did have that theory, maybe we could begin to ask the question, could alternate universes make some imprint on our own universe? Or even, can you get to an alternate universe by going through a black hole?
Okay. So some, I won't say many, but I'll rephrase that to some cosmologists and astronomers use the concept of the multiverse in explaining why the universe is so why we're here now, so fine-tuned for life, and why we're here. So how? So obviously you're not a particularly supporting fan of multiverse, but how would you sort of reason?
No, I'm not a fan of. I'm not a fan of many worlds. I'm not a fan of the idea that the universe splits itself on every quantum decision that it has to make, because there's quite a lot of quantum decisions around there. That must mean, and just the idea that the entire universe would bifurcate rather than make a simple choice on which way an electron goes is just nuts. Whereas the multiverse is a very different concept. The multiverse is just the idea that that our universe isn't the only universe, that you could have disconnected bits of space and time, complete other universes, perhaps with their own set of physical constants. And again, it gets very philosophical, because then it becomes, you look at the fine-tuning of our own universe, and really it's a very strange place. I think someone once described it as somehow it looks like the universe knew we were coming, in that it's very difficult to make a universe where you have long-lived stars, where you have the possibility of life. It's a really very strange kind of universe.
In these other universes, you wouldn't, for example, be able to have a different constant for pi or something. Like, there are some things which are mathematically fixed.
Oh, that's hilarious. Pi isn't fixed.
Oh,
If you curve space-time, then, so if you go to, I have an inflatable moon. I used to teach general relativity. So if you have a sphere, so pi is the ratio of the circumference to the diameter. And so if you take a sphere and you go around the equator, that's 2 pi r. And if you go across its diameter, going up to the pole and down again, then that's pi r. So the ratio of circumference to diameter is 2. It's very easy to, when you're in a curved space, to have pi not be pi.
So you don't think that the physical constants are all interrelated in some way? That there isn't some way to fix them?
Actually, I think there probably is some physics that fixes some of the physical constants. At one point, I taught Introduction to Astronomy, which was kind of astronomy for poets, and I made my students do an essay question, which was the fine-tuning of physical constants in the universe argues either for a multitude of universes or for a god. Discuss. And the ones who were doing it as scientists for an easy option were just kind of like, oh, what? I'm going, I warned you, I would ask a real essay question. I want you to discuss.
It was hilarious seeing them.
What side of the debate did they come down on?
Well, what actually amused me was that they had taken that dichotomy of positions rather than saying, why not have both? Why not say, in the same way that looking at this physical universe, I'm also a Christian, so I look at the physical universe, and the more I know about the scale of the universe, the bigger it makes God. So, maybe a multitude of universes, why not? It just makes your concept of God bigger.
Someone's got to throw the cosmic dice to start with.
But they didn't seem to want to. I'd kind of set it up as a dichotomy, and so they'd kind of gone that way, even though they were, the scientists really didn't want to touch this question with a barge pole, and I was just is that they didn't just step back and look at the assumptions and think, well, okay, why is it either or? Why can't I have both and? And sometimes people think that about science and faith. They think it kind of gets set up in the media as a dichotomy, and a lot of people seem to not step back and think, oh, well, why can't you have both?